Recording is rolling. So today is Tuesday, October 18th. I'm going to take today and tomorrow to do as many problems as I can with you guys. I've got some other demos I might slip in probably tomorrow, but today let's just do as many problems as we can. Okay, so I find a bunch from chapter 7 from your college physics textbook. Uh, and I think you guys should be able to actually do these all by yourself at this point. So what I'll do is what I normally do. I'll change the numbers, but I'll keep the scenarios the same. So you have one extra practice set to look at. You guys know all the solutions, of course, are already posted online. And that's for the numbers that you have. And I'll try to keep a kind of a fast pace just because, again, I think you guys should be able to solve these by now. Or at least that's my plan. Okay. Okay, so first one is number 5. It says the dentist drill starts from rest and after so many seconds of constant angular acceleration. Okay. Now you guys know what angular acceleration is, right? So think about turntable. So it starts to spin, it spins faster, faster, faster. Right? And the rate that it picks up speed, because right now you guys are looking at constant angular velocity. But if I speed it up, right? If it speeds up at a constant rate, then that's angular acceleration. We've been designated that with Greek letter alpha. Okay. And then, it picks up to, they told you the speed picks up to, but they told you in revolutions per minute, which notice is not radians per second. So we're probably gonna have to do some conversion there, right? The dimensional analysis. Okay, so find the drill's angular acceleration and then determine how far it's turned during this time. Right, so number 5, I'm going to say the time is like, let's say 2.5 seconds. And let's say omega final is, now 2.51 times 10 to the 4. That's like, what's that? 25,000? 25100. Yeah, and that'd be revolutions per minute. Okay, so I'm going to make a different number. I'm going to go with, how about 35,000 revolutions per minute. Right? Right. They also told you it starts from rest. So, hey, it starts from rest. It goes up to this angular velocity in this much time. Isn't that 3 kinematic values? Right? Like starting from rest is the one I didn't write down. Right. So you could solve this. Okay. Now, okay, this conversion here. I know that 1 minute is 60 seconds. And I know that 1 revolution is 2 pi radians. Right? That all be true? Okay. And so revolutions goes away, minutes goes away. I've got radians per second. Is that right? So 35,000 times 2 pi on 60. Okay. So this is the same thing as 3665. That'd be radians per second. And radians per second is a number that I can actually feed into formulas, right? Like this kinematic formulas up there on that sort of beige yellow poster, right? Which is the same 3 kinematic formulas that, got haywire because I know we had a standardized test last week and oops, right? Did I put them up? Anyway, they're not there. Right, but you guys know. Right, so we're going to go. We're solving for alpha, right? Can I go final omega is equal to initial omega plus alpha t? Okay, because that would have everything except for what I'm solving for there. Right? So this number is so many radians per second. It starts from rest. We're solving for the rate that it's picking up in radians per second squared, and it did this all in so many seconds. Like that? Okay. So can I just take that and divide by that and get the answer? Okay. So alpha equals, looking at, that'd be radians per second divided by seconds. That's radians per second squared. Right? That be right? Okay. And that was part A. Part B was determine the angle in radians that it turns. Right? So how far is it turned? This is analogous to like how far have you walked in meters. Okay? That was part A. So part B, we need to solve for theta. And I have a couple of options. I could either use theta equals omega naught t plus half alpha t squared. Okay. Or if you want to, you could go omega final squared equals omega initial squared plus 2 alpha theta, right? So this is probably the most straightforward way, right? So 1/2 1466 radians per second squared. Right? Remember, I can only apply these formulas at all because I have everything's in like radians per second squared in this case for alpha. Okay? And the time interval is the same as it was back in part A. So you just pop in that time interval. Okay? Who has any questions where I got any of these numbers? Anything? Okay. So this is 4581 rate. Okay, so many radians, right? We throw in one more twist, which is you could divide this by 2 pi and convert it to revolutions, couldn't you? Right? So to do that, here, what if I take 4581? So it's that many radians it's turned, right? Okay. Can I do this? Can I say divide by 2 pi like that? And how many revolutions? Who sees how I typed this wrong on my screen? There's something wrong with that. What's wrong with that? Yeah. So, exactly. You guys catch that? Right? If you get great. So this calculator is going to divide by 2, and this is going to turn around and multiply by pi. Right? So exactly. Right? I have to add this in parentheses. Right? Most guys probably do that just in case, right? So another way to quantify this is 729 revolutions. 729 rev. Right? A little bit different way to think about it. Okay. Right. Everybody right? Number 15, a car traveling eastward turns north by going on the circular path. Okay? Look, it looks like a quarter of a circle here. Okay? They told you the length of the arc and the amount of time it takes for the car to turn. Okay? And 2 questions. How fast is the car traveling? Okay, well, it'd just be distance divided by time to give you speed. Okay, go ahead. Okay, the angle in radians that it turns. Okay. So this is analogous to x equals 1/2 a t squared, except that theta equals 1/2 alpha t squared. So t is still t, but okay, instead of x it's theta and instead of a it's alpha. Okay. Okay, so just take your answer from part A, which shows you the rate that it's speeding up. Feed that in. They told you how much time it goes for. I can tell you how far it's turned. Okay. Now, key to the formulas is everything's going to be in like radians per second for how fast, and radians per second squared for like the rates picking up how fast. Okay? So radians is how far it's turned. Okay? Now, you could have done this a different way too. Okay? So the answer is what, 4581 radians? Okay? You could have said omega final squared equals omega initial squared plus 2 alpha theta. Isn't that analogous to vf squared equals v naught squared plus 2ax? Right? I could have solved this way. And you should get the same answer. Okay? So this number is still 0. So this goes away. But you have to solve for those first. Okay. Good. But you can do this real fast. I'll just show on my calculator screen. Because if you know it's picking up 1466 radians per second squared, and you do that for 2.5 seconds. Okay. This would bring me up to this number is 3665 radians per second. So that's how fast it's going. Now, first you have to square that, and then divide by 2, and then alpha is 1466 rad per second squared. Okay, and you can solve for theta that way. Okay? Take that divided by that. Okay, so 3665 squared divided by open parenthesis 2 times 1466. Okay, they should get the same answer, 4581 radians. Okay, and that's exactly what I got before using. Okay, so there you go. 2 different formulas, 2 different paths through the forest to get to the same answer. 4581 radians, 4581 radians. Okay, so got some options. Okay, so that's just rotational kinematic motion. Okay, so that's a lot like what we did in Unit 1, except it's just rotational instead of moving forward in a straight line. Okay. Okay. So everything. Okay, 15. So let's check out this car. We know how far it goes, distance, and how much time. We have to figure out how far is the car going, and then something about its the acceleration, like centrifugal acceleration. Okay, so I'll also have a quarter of a circle turn for same picture. I'll use the same picture. Wait a minute. Oh, okay. All right. But I'm going to change the number. So I'm going to say that the distance my car goes is like 500 meters. And I'll say that the time that it takes to turn is like, let's say 40 seconds. How about that? The numbers are kind of close, a little different. Right. In fact, you know what? Looks like my car goes to a lot further distance and a little bit bigger time. Right. So I bet my acceleration is not going to be as extreme as the book example, right? Right. So, like, you know, if you're like going around a curve, you can like feel the G's if you're in the car. I bet mine's not going to be quite as extreme. Right. So, speed is just distance per time. So you take how far the car went, the distance, divided by the amount of time. And you get the speed. Right? Now this is in meters per second. Right? I think it's about 30 miles an hour. But anyway, that's high. Right? We got meters per second. That's what we care about. Okay? And second question, what is the magnitude and direction of the acceleration? Because acceleration is a vector. Right? Of the car at point B. Right? Now, there's different kinds of acceleration. So make sure everybody knows exactly what they're talking about here. Guys, if the car's going at constant speed, right, the speedometer is just pointing it, in my case, like this number of meters per second goes, it's not really moving, right? Does the car have any tangential acceleration? The answer is no, right? You have to either be slamming on the gas pedal going, or slam on the brake, to have some kind of tangential acceleration. But you can totally go on constant speed, but if you're changing your direction, you still have a type of acceleration. It's just centripetal acceleration, right? Okay. So I can tell you the direction of the acceleration is just pointing straight to the center of the circle, right? Okay. And that would be caused by the friction force between the tires on the road. There's a friction force acting on the mass of the car that causes a centripetal acceleration, which always points to the center of the circle, right? Whenever you're going around a curve. Right? And that's the only type of acceleration in this case, only that centripetal, right? And you can quantify that. So say this is part A. Okay. You can quantify the centripetal acceleration as v squared over r. Isn't that straight off your AP equations? Okay, point out to you. Okay. So here it's right. It's kind of near the top, right? It's right here. You guys remember that? V squared over r. Okay. Right. So I can take that speed. Yeah. Now, of course, it has to be in meters per second, but that's good. We already got that. Right. Square that and divide by the radius of curvature. Okay. Whoops. I don't have that yet because right, they told you how long the arc is. So we're going to have to do a little bit of circle math and come back to this. Right, so let me go off on another venture over here. Right, so I got a quarter of a circle. Okay? And from here to here, I'm saying that this distance is 500 meters, different from your textbook numbers. That's just my numbers, right? From here to here, right? So can I say circumference equals 2 pi r, right? And I would really like to know what this r is, right? What is this r so I can feed that into a formula? Isn't that true? I'd really like to know that r. Okay. Okay. And I do see that 500 is a quarter of a circumference. Can I do this? Divide both sides by 4. Right? And this whole expression is just equal to the 500 meters. Okay. Probably not the only way to do that. That's one way to do that, right? This is a quarter of a circumference. You guys get it? And so I got 500 meters is equal to, say, 2 pi over 4 all times r, and I'm solving for r. Okay? So I could take 500 meters, multiply by 4 on 2 pi. It's some version of that. Is that okay? Okay. That can tell me what the radius of the curvature is. Okay. Okay. So geometry here. Okay. I'm looking at 318 meters. That's just my notes numbers. Okay. That doesn't align with the textbook. That's just my notes. Okay. 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 So now I know the radius of curvature. Okay. Well, now that I know the radius of curvature, now I can go back and complete this, right, which is set up to start. Right? I know how fast you're going. Radius of curvature is this many. Oh, what? Oh, yeah, okay. That many meters. That. Okay. Now, when you guys did the lab version of this, right, you actually did mv squared over r to get a centripetal force. Okay. But remember that top plate of canister like had some radius of curvature. You held the meter stick and you directly measured it, right, in your lab. You guys good? Okay, so let's get a number, 12.5 squared over 318. Okay. So I'm looking at this many meters per second squared. Okay. Ooh, no, very good. That's very close to half a meter per second squared, isn't it? Okay. Suppose I round it to about half a meter per second squared. Okay. Now, in the back of my mind, I also know that G is about 10 meters per second squared, or 9.8, 10. I think it's the same ratio going on here, right? Okay. So, what's like the G force? Like, not really a force, but like how many G's would my driver feel? Say, what is half a meter per second squared compared to 10 meters per second squared? It's 0.05. It's like a 20th of a G, right? Now that's completely lateral, right? So yeah, you feel the full weight pulling you down, right? But if you're interested like laterally, how many G's? It's like a 20th of a G, okay? Just laterally. Is that right? Okay. Number 16. It's been suggested that rotating cylinders. Oh, hey, that's like your guys' O'Neill cylinder up here, right? Space Colony used its colony. What angular speed must such a cylinder have so that centripetal acceleration equals the free fall acceleration on Earth? Hey, we've been setting up problems like this, haven't we? Right? Like if you know how big it is, can you figure out how fast it has to spin? Right, whole deal. Okay, weird side note here. You see, it has like 10 miles long and 5 miles in diameter. This is kind of a technical thing, but that actually would not be stable because of a really weird property called the intermediate axis theorem. Okay, let me do this because I just can't help myself. Can't undo this. Okay. You guys got cell phones, right? Okay. Some of you guys probably know about this. You guys know if you spin it this way, you can spin it this way, like no problem, right? It's this like you got a small space to work in, but you guys you do that. I bet you guys could spin it this way, no problem, right? Okay, just spin around. Okay, something like that. But I'll tell you what you can't do. Okay, hold it like this and like flip it around like this. One complete turn. Okay, just like it's not gonna work. Right? It always makes like a weird like here you can try it, but it's never gonna make a clean turn around like this. Right? And there's a whole you can look this up on the internet learn all about this, but there are only some axes that can find about that's actually stable. Okay, and like this one, it would just fail this. So NASA engineers have figured this out too. Okay? So you actually want your O'Neill cylinder shaped more like the one you see in class, more like I've been drawing on, like this, where it has a really wide diameter compared to like how long this is. Anyway, okay. Anyway, let's get some numbers on the board here. They told you now to do the calculation, you actually don't care about how long it is. You just care about how its radial value. They told you its diameter in miles. Okay? So I'll come up with the diameter in miles. Okay? Let's say my diameter is, I'll do 12 miles. How about that? 12 miles. Okay. Okay. And you also know your target gravity. So if this thing is spinning about this axis, okay, it's got some omega. Okay. Well, that's what you got to figure out is how fast does this thing have to spin? What is its angular speed? How fast does this thing have to rotate? Okay. About this axis. All right. So I really care about the radius, and also know I need meters, right? So let's turn miles into meters. Well, I know that 1 mile is pretty close to like 1.61 kilometers. It's pretty close to that. Okay. If you want an exact conversion, 1 inch is defined as exactly 2.54 centimeters. So if you want to get like super granular, but it's pretty close to this, pretty close to the golden ratio, kilometers to miles. Okay. And then 1 kilometer is 1,000 meters. Okay. So I can convert and figure out how many meters is this. Okay. Now that's the diameter. So then if I divide that by 2, I can get the radius, right? So that diameter, okay, I'm looking at this many meters per diameter. Okay. Divide that by 2, then get the radius. So therefore, radius is half the diameter, which is this many meters. Okay. So now I know the radius of this O'Neill cylinder, right? Now, all these people standing on the inside surface, right? Remember how the mechanics of this works. As this thing is rotating, see if the walls fell away, they'd fly off tangent to their motion, right? Right. But there's a wall there that's preventing them from doing that. That's providing a normal force holding them in, which is acting as the centripetal force, right? And all these people might have different weight, different masses and different normal forces, but they all experience the same centripetal acceleration. A centripetal acceleration, you could say, is v squared over r, but there's an easier version of this to use for O'Neill cylinders, which is what? Not v squared over r, but omega squared times r, right? Of course, they lead to the same answer. Right? Just this way is a few extra steps. This way is a lot faster to solve. Because the question's being asked, that right there, isn't it? Right, so what's your target acceleration? Yeah, sure. 9.8 meters per second squared. You said 10, that'd be fine for you. Pick your favorite. Okay. And then radius. Well, I got this radius. Right. You guys have a different radius from your textbook. Got to figure that out. Okay. And I did that conversion to get it in meters so that all the units are consistent. Because if you run calculations and calculate, right, you want all the units to be consistent. So 2 algebra steps. Again, divide this over and take the square root. I'll go ahead and pull the unit out. It's going to be radians per second at the end of the day. So square root. Woo. Okay. So a tiny number of radians per second. There you go, just like that. Now, since that's a tiny number of, it's kind of weird abstract unit. Let's do this. If I times 180 over pi, I can say that's the same thing as 1.82 degrees per second. Right? It's a little easier to visualize, right? Because that's about 2 tick marks every second. Right? It's rotating. Right? Oh, like this. You see it in space. Right? And you know what else I'm curious about? I wonder how long it takes to go around once. Right? So you can play off either of these numbers. Right? I'll do this one. Okay. So wouldn't 2 pi radians be 1 revolution? So if I take my 2 pi radians, right, so there's 1 revolution, right? 2 pi radians, and I divide by 0.032 radians per second, that would tell me the number of seconds it takes to go around once. Okay? 196 seconds, which is also called like 3 minutes and some change, right? 3 point something minutes. Okay. Okay. So my O'Neill cylinder, just the numbers I came up with. Okay. Take this a little over 3 minutes to go around once. Okay. That's what you would want for everybody to feel like they're on Earth. Okay. You guys good? Number 18, adventurous archaeologists. They give you his mass, tries to cross a river by swinging on a vine. The vine is this many meters long, and the speed at the bottom of the vine is this many meters per second. Okay. Now, pause right here. Do you guys think if you guys could calculate this if you were given like the starting angle or how far he falls or something? You could probably calculate this, right? You could do that using Unit 1 information. You could also use this using something we haven't covered yet, conservation of energy. So yeah, keep that idea in your back pocket. Okay? The archaeologist doesn't know if the vine has a breaking strength of 1,000 newtons. Does he make it cross over without falling in? Right. So we can do a quick calculation. What if he was just hanging at rest? Because if he has a mass of like 85 kilograms, what is his weight in newtons? Pretty close to
850.
Yeah, 850 newtons, right? M times G. Okay, 850 newtons. So can a 1,000 Newton vine hold 850 newtons of weight? Yeah, so that'll work. Okay. But how many guys think if he's swinging that there's an extra tension to provide a centripetal force and the vine might break possibly, right? Ooh, like extra force to, if it's like a swinging motion, right? All right, so we have to consider that too. All right, so let's go 18. Back up here. So I've got this vine. That's gonna go through this tight motion. Okay. Now the length of the vine is the same thing as the radius of the circle, isn't it? Okay. Yeah, well, it's just a capital R. How about that? It's like fixed value. Okay. Uh, they gave you 10 meters. I'm gonna make mine how about 14 meters? How about that? Okay. Put the sky right here. Right. Oh, I'm gonna call the mass of my guy 65 kilograms, and I'll have T max equal to yeah, I use the same T maxes in the book. Right, how about that? I wonder if my guy's gonna make it. Oh, no. Here's where. If you do this angle, do you think you do some trigonometry and calculate like the height change here? Have we ever done anything like that? Like if I tell you so many degrees, like this might be 40 degrees, you can calculate this height change. Right? And you could go back to unit one and say, like, if you know the height change, it ends up being square root 2gh if you just start from rest. Right? Right? But when we get conservation of energy, this is going to come back to you. But anyway, we're going to cut through all that. Suppose we figured this out all out already. And I'm going to have this guy go in V equals, I'll say 6 meters per second. How about that? At the bottom. Okay. So, but in the future, I'll have you guys solve that, based on this angle. Okay. All right. So let's figure this out. I need to know free body diagram at this point when he's swinging at the bottom. Okay. Free body diagram. Now this guy has a weight, mg. Okay. Now, if my guy is 65 kilograms mass, I bet he weighs about 650 newtons, right? Is that true? Okay. Now, if he's at rest, then the tension force would just balance that out. So it'd be 650 newtons. But the fact that he's swinging, are you going to make this tension greater than 650 newtons? Yeah. Okay. I'm going to do T with a little vector to distinguish it from time period, because T could be a vector tension. Okay. Notice I made this vector up greater than this vector down. You guys see that? So is this guy in equilibrium? No, there's a net force on him. Right? There's a net force upward. Right? In fact, this minus this, which would be the net force, right? You guys see how it's going to point to the center of the circle, right? There's like a curvature here, like a circle. Right? Because there's a centripetal acceleration. I'm on a curved path. So I'm going to say the net force is equal to, well, yeah, how do I do this? Let's say mass times acceleration, right? There's Newton's second law of motion, right? That equals mA, right? Now the net force, isn't that the difference between the tension pulling up and his weight pulling down? Equal to mass times acceleration. Okay. Hey, does this look a lot like tension in an elevator table? Right? We set this up and went a different way with the story back a couple weeks back. Okay. But this acceleration, don't we care about centripetal acceleration? Can I substitute in for this A, like V squared over R? Because I have a V and I have an R. Is that true? Okay. So the difference between the tension pulling up and his weight pulling down is M V squared over R. Right? Substitute in that, because that is what the acceleration is. It's centripetal acceleration. Hold them in a circle. Right? Is that right? All right. So I'm trying to figure out what is the tension, what is the necessary tension for like this scenario, right? And then if it's greater than the maximum, the bind is going to break. And if it's less than maximum, then he's going to be okay. He's got to sail through. Okay. Right. So what is this tension? Okay. Well, I know his weight 650 newtons. Yeah, I've got too much crammed into that corner. I got to break out a new paper. Symmetry. So tension minus weight equals, so there's the net force, which is the centripetal force. Right, just like that centripetal force. Okay. I know his weight's about this many newtons, and his mass is this many kilograms. His speed, I've got this many meters per second, and that's being squared, and then divide by a radius of curvature, which is like this many meters. Right? So, okay, so now I'm just like feeding numbers in. Okay. We gotta add this many newtons over. Well, but right before I do that, we gotta figure out what all that fun fraction stuff is first. That times that over that, like that many newtons, right? Okay, so add this over. Okay, and I'm getting the tension at the bottom is going to be this many newtons, right? Now, again, I just made some numbers on the fly, and this is what I got. Okay. So is my adventurous archaeologist going to be able to make it through the swing? Yeah, yeah, because this number is less than T max of 1,000. Right. So my guy's okay. How much your guy did your guy make it through? Yeah, I think your guys' line breaks, right? Because okay, okay. Guys, good. All right. I know I'm going kind of fast. Anybody got any questions? All right. Number 27. Actually, we did 27 already, didn't we? Did we do that? Is it okay if I skip 27? Does anyone have any questions on 27? This is basically your guys' lab. And also, we did that one the other day too. Number 32, a roller coaster vehicle. Okay. See the roller coaster going through the valley and then over a mountain right here? Hey, if you're going through the valley, what do you feel? Very light or very heavy? Very heavy. How about the top of the mountain? You feel very light. In fact, if you're going too fast, you think the train goes fly out. You don't want this much excitement, right? If the vehicle has a speed, okay, so they told you the speed at the bottom. What is the force on the track at that point? Like the normal force. Okay, let's do that first, then we'll other stuff later. Okay. So got this roller coaster. Right. All right. Now focused on. We've got a radial size. Okay, they said 10 meters. I'm going to change it like 12 meters. How about that? Okay. Okay. And right down here at the bottom, I'm thinking this is probably going to look a lot like that adventurous archaeologist. There's going to be some weight and there's a normal force, and the normal force is greater than the weight. Okay. Okay. What is the force of track? Oh, they told you the mass. Okay, that's what else they gave you. Okay. So I'm just going to take a single person riding, right? Now let's call him how much my archaeologist was 65 kilograms? I'll call my passenger 65 kilograms, right? I'll just focus on one passenger. Right? So we got mg down, we got force normal holding up, right? Okay. And actually, I think it's going to be a lot like that archaeologist, where the net force is mass times acceleration, and there definitely is a net force, isn't there? That net force is the difference between the normal force acting up, which is the question, and the weight acting down, kind of result in ma. But that a, isn't that it's going to be v squared over r? It sure does look a lot like, right? Swinging on the vine, right? So now it's a normal force applied by the track. That the math looks a lot the same, doesn't it? Okay, so they must have told you the speed going through. They did give you speed. Oops, I forgot to label that. Okay, they said so many meters per second down here at the bottom. Okay, so they add a speed in here. I'll go v equals about 15 meters per second. About that. So the speed is like 50 meters per second. Okay. So got all this. Then I can just feed these numbers in at this point and solve for the normal force. Right? So mg, that's going to come out to like this many newtons, or pretty close to. I got this many kilograms. I got this many meters per second. Then I'm squaring, and then divide by radius of curvature in meters. Okay. So I've got all base SI units. Oh, yeah, go ahead. R, they gave it to you. Okay. Now, your book says 10 meters. Right, and mine, I just made a different number. Okay. Okay. So and that has to do with like the radius of curvature. Like, so if you were to fit in a circle, it's like flush to the curve here, right? See how it matches the picture? It's like flush to the curve, right? Yeah. So like when you guys are going around a curve in your car, you're like, there's like a curvy road. That similar idea. There's like some circle you could fit that's like flush to that curve, right? That could represent what you're going for. Right. So it's just mass times v squared divided by r is this stuff, then add the weight over. Okay. Oh, hold on, there's something wrong here. Right. V squared over R. 15 squared divided by R. 65. Okay. I typed something wrong earlier. Right? Plus 60. Yeah, that looks a lot better. Okay. So normal force from the track is, it should definitely be something larger than the weight of, well, the passenger or the cart, right? Bigger than the weight, okay, which is the initial setup. That vector is bigger than that vector. Okay. Is that right? Okay, that's it. All right. Aha. Question B, what is the maximum speed the vehicle can have at point B? Now we're going over this hill. So it still stays on the track, right? Now, whether you look at the car as a whole or a single passenger, the mass is going to cancel out at some point. Let me do a demo for you guys. Demo time. Here it is. Aha. Right, so if you're watching a video at home, what's this? Got a cup with a string on it. Ooh, got water. This is going to be exciting. Okay. And then off screen here, I'm just going to turn this upside down so the water doesn't fall out. Right. Right. So if I get this going fast enough in a vertical circle, right? So if you're watching a video at home, just flying this around in a vertical circle, but the water's staying in the cup, right? Hey, do you think if this going around too slow, at some point the water's going to fall out? Huh. I wonder what the minimum speed is to keep it in. Okay. So this question we're about to tackle is like mathematically identical to that. So, except, well, okay. So let's blow up that point where cart's like going around the track. Okay. And I know that there's a weight pulling down, right, mg, right, because Earth is always pulling down. Okay. But if it's going at just a speed where it's about to fly off the track, that it just barely stays on, then what is the normal force approach? Does the normal force approach zero? I think it does, right? Like this normal force is going to get less and less and less until it eventually just goes to 0 newtons, right? And then right at that point, that was it, right? And then for the case of the water in the cup, it's the same story as this, that the weight is acting as the only force that is the centripetal force, right? So the centripetal force is provided by the weight, right? You know where else you've seen this is like orbits, right? It's the same idea as orbits, except instead of mg, I did the full gmm over r squared, you know, raise the Earth, mass of the Earth, the whole deal, right? This is just a simplified version of that, right? Mg is, right? Because we're stuck at the surface of the Earth, right? If you're at the surface of the Earth, you can use little g like this, right? All right, but centripetal force. You can either do m omega squared times r, or you could do mv squared divided by r, depending on what you're looking for. Right, so I'm going to do mv squared over r because I'm trying to solve for the linear speed for this to all be true. Right? Is that okay? Is that okay? Now again, there's like some circle you could fit flush to this curve at this point that has a radius. Okay? They gave you a radius of like 15 meters. I'm going to change that. So what if my radius is like, let's go 19 meters. Right? So I have a little bit bigger circle than you guys. Guys, the fact that I have a bigger circle, can mine go faster or slower than yours to just barely stay on the track? I'm thinking mine can go a little faster. How about this? What if the radius was like the radius of the Earth was just like basically look like a flat plane, right? Then couldn't mine just go extremely fast? I could go up to 8,000 meters per second before it started orbiting the Earth, right? So I bet my answer is going to be a little bit bigger than your answer. That's what I'm trying to say. Right? Do you guys see the mass cancels out? Right? And the same was true for orbits, right? So like International Space Station, right? Go out on a spacewalk, right? Drop this outside, like, whoa, I dropped my kilogram I just brought to space, I guess, right? It's just going to float alongside, right? Okay, so it doesn't matter what the masses are, cancel out. Okay. Okay, so everybody's going to fly off the track at the same time. Cross multiply the r and take the square root. Wouldn't the speed be the square root of g times r? Okay. Gravity field of the planet. Radius of curvature of this circle, right? Great. Which, you know, like an orbital velocity case would approach the radius of the planet. All right, that's that. Let's pop in some numbers. So I got 10 meters per second squared. Okay, and we got a radius curvature. Well, I'm gonna go with 19 meters because this number I just made up, something like that. So it's a square root of 10 by 19. Okay, I'm looking at 13.8 meters per second. So if my roller coaster hits 14 meters per second, well, that's bad news for everyone ride my roller coaster because they're fly off the track. Okay, but if they're going like 12 meters per second, they're going to be okay. Just barely, they feel like almost weightless. They want like 12 meters per second. Okay, you guys good? All right. And then an AP style question they might care more about like proportions. They say like, suppose you quadrupled the radial size of the circle, right? So you just make the track a lot flatter, right? If you quadrupled R, wouldn't it become a lot flatter? Okay. They say what speed could you go then, you know, proportionally. So guys, if you quadruple R, then speed can increase by a factor of what? 2. Yeah, you could go twice as fast and then also like almost fly off the track. Okay. So, okay. And you could go the other way. If you have like a quarter of the radius circle, so you have a really tight circle, you could only go half as fast before you're about to fly off the track. Okay. Number 37, objects with masses 70 kilograms separated by this distance. Find the net gravity force exerted on these objects on a third object placed midway between them. Okay. Okay, and then there's another question, but let's do that one first. Okay. So this sounds like pretty much straightforward, just universal gravitation. That we're gonna have 3 objects. Okay, so it's gonna be a little more fun now. So 37. Zoom out. There we go. All right, so I need an axis on here. Okay. I'm gonna put an object here. I'll call mass A is 100 kilograms. Yeah, my numbers are different from your numbers. You guys get the idea, right? Okay. I'm gonna go mass B is how about 250 kilograms. Okay. And then it told you separation distance. So from here to here. But they did put an object that was like geometrically right in the middle, right? So I got mass C. I'll use the same mass C as you guys have, like 50 kilograms. Okay. Okay. Now, they told you this full separation distance. So can you just divide that by 2? Go like boom, boom. Right? So suppose we got like 0.70 meters and 0.70 meters, something like that. A second. Okay. Let me pause this and we'll figure out what's going on here. Pause.